Okay, in section 5.3, we are going to solve trig equations, which we started doing in chapter 4 on a kind of basic level. Okay, so for the first example, it's very similar to what we did in chapter 4, except we do need to isolate the trig function first. Okay, so I'm going to try to isolate the cosecant, and then I am going to solve for the domain of 0 to 2 pi. Okay, so what am I going to do? I'm going to move the 3 to the other side. So I get 2 cosecant x equals 4. If I divide by 2 on both sides, cosecant x equals 2, which I will use the reciprocal of. So the sine of x is 1/2. And then I just have to think between 0 and 2 pi, where on the unit circle does the sine of x equal to 1/2? Okay, in my head, I'm thinking it's going to be right here and right here. So x will be pi over 6 and 5 pi over 6, and those are the only two x values that satisfy this equation between 0 and 2 pi. Okay, example 2 will be very similar, except for there's no restriction that it does have to be between 0 and 2 pi. Okay, so we have to include all possible answers. Okay, but I am going to try to isolate the sine x. See, what am I going to do? I'm going to minus the sine x on the left. I'm going to minus this over to here. You could do it differently. Then I will have root 2 equals, and if I minus the sine x to the minus sine x, I get minus 2 sine x. Okay, so if I divide by -2, let's see, I get sine x equals negative root 2 over 2. Okay, so I'm going to figure out where on the unit circle the sine is equal to negative root 2 over 2. And I'll try to expand this for all real numbers. Okay, if I were restricted to 0 to 2 pi, it would happen at 2 locations on the unit circle. Okay, but I have to take into account all possible coterminal angles to those 2 locations. So one of the locations is 5 pi over 4. Okay, but it's also every coterminal angle to 5 pi over 4. So to account for that, I say plus 2 pi n, and I'm going to assume n is an integer. Okay, where else? This also occurs at 7 pi over 4, or you could call it negative pi over 4. But again, every coterminal angle to this is also satisfies this equation, so I have to add 2 pi n, where we assume that n is an integer to capture all the coterminal values. Okay, let's keep going to number 3. Example 3, 3 tangent squared x minus 1 equals 0. If I could factor that, I mean, in theory, you could factor it. If you would like to factor it, you can. I'm going to solve using square root, but it is a quadratic, so I should expect 2 values for tangent. Okay, let me start by adding the 1 to the other side, and then I'll divide by 3. So tangent squared equals 1/3. Okay, now if I square root both sides, I get tangent x equals plus or minus the square root of 1/3. Let's see, the square root of 1 is just 1, so let's get rid of this. Okay, so plus or minus 1 over root 3. Okay, now let me think. I could rationalize it, but I think it's easier to leave it as is, and this is not my final answer anyways. If I leave it like this, it's easier for me to tell that the y value is going to be some kind of 1/2, and the x value will be some kind of root 3 over 2. Okay, so the y value is going to have a 1/2, the x value is going to have a root 3 over 2, and because it's plus or minus, it could be here, 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 or here. Okay, there's a couple ways to express my answer for this, and that's because tangent has a period of pi, which is a little different. Okay, so one location on the circle is pi over 6, that satisfies this equation. Okay, I want to include all the coterminal angles to this and any equivalent angles. Okay, but because the period of tangent is pi, if I add pi to this, I end up over here at this next location. So if I add, instead of adding 2 pi n, if I add pi n, then I've included 7 pi over 6, and I don't have to write 7 pi over 6. Okay, if you would prefer to write pi over 6 plus 2 pi n and 7 pi over 6 plus 2 pi n, you could also do that. That would give me the same result. Okay, now I'm going to consider 5 pi over 6. Okay, the same is true of 5 pi over 6. Because the period of tangent is pi, if I went pi around the circle, I would end up at 11 pi over 6. So if I add pi n, I'm including 11 pi over 6 as a solution, plus any other angles that are coterminal to either of those. Or I could write 5 pi over 6 plus 2 pi n and 11 pi over 6 plus 2 pi n, and that would be an equivalent answer to that. Whichever way you prefer is fine with me. Okay, let's try example 4. No domain restriction, just a different strategy for solving. Okay, let me see. I'm looking at this 2 cotangent x sine x minus 3 cotangent x. I notice they both have a cotangent x. I'm going to factor the cotangent x out. I don't want to lose it though because it is probably important to the equation. Okay, if I factor 2 cotangent or just cotangent x out of the first expression, I'm left with 2 sine x minus, and if I factor cotangent x out of the second expression, 3. Okay, since it equals to 0, I can use the zero product property, which will tell me that cotangent x equals 0, or 2 sine x minus 3 is equal to 0. Okay, let me rearrange this. Okay, now if the cotangent of x is 0, this is the x over the y, so it's where the x values are 0 on the unit circle. Or that'd be 0, 1, and 0, negative 1, down here and up here. Okay, again, there's more than one way to write this because cotangent and tangent have a period of pi. So one way would be to say this is pi over 2, and I could do pi n because the period of cotangent is pi, and by adding pi, I'm including this as an answer, and I'm including every coterminal answer to that. If you prefer to list it twice, you could do pi over 2 plus 2 pi n, and 3 pi over 2 plus 2 pi n, or something like that. Okay, now let me consider my second expression, my second equation. I have the sine of x equal to 3/2. That's a problem because the sine of x can't be higher than 1. So sine x cannot equal to 3/2 because that's going to violate the range of sine. Okay, so that factor didn't work, but this one did work. So this is all the answers that would satisfy this equation. Okay, example 5. It's equal to 0. It's a quadratic. I'm going to have to factor it. So this is just to show you a factoring problem. Okay, use whichever method you normally do to factor these. Remember, this is like 2u squared plus u minus 1. Okay, once it's in factored form, and it's because it's equal to 0, I can use the zero product property, just that each of these factors is equal to 0. So if 2 cosine x minus 1 equals 0, then cosine x is equal to 1/2. If cosine x plus 1 is equal to 0, then cosine of x is equal to negative 1. Okay, no restriction on my domain, so I have to include all the coterminal angles. Okay, cosine's 1/2 is going to be here and here. So that is pi over 3, and because the period of cosine is 2 pi, it'll be 2 pi n. We're assuming that n is an integer. The other one, 5 pi over 3 plus 2 pi n. And then for the cosine is negative 1, that's going to be over here, and that's the only one. So pi plus 2 pi n. Okay, and that should include all the values, including the coterminal values that satisfy that equation. Okay, now example 6 is just to show another strategy. Okay, example 6, I have cosine x plus 1 equals sine x. I don't have matching functions. I don't have a common factor. I don't have any squareds, because if I had a squared, I could use a Pythagorean identity. Okay, so I'm going to have to make something happen here. This happens occasionally, and as a last resort, you could square both sides. The reason I'm doing that is to create some kind of Pythagorean identity. Okay, the only problem is if you square both sides, you create extraneous solutions. Okay, so I'm going to have to check for extraneous solutions at the end. Okay, so that's why I only do it if I can think of nothing else. Okay, just like if these are radicals, if I square both sides, I create answers that are not true. Okay, now if I do cosine x plus 1 times cosine x plus 1, make sure you distribute it all out. Cosine squared x plus cosine x plus cosine x is 2 cosine x plus 1 equals sine squared x. Okay, now you might think, well, this does not look much better. But because there's squareds in it now, I can make a substitution. Okay, it's just a matter of which one. Okay, I have cosine squared plus 2 cosine x. I have a lot of cosine here, so I'm going to leave this alone. And then I have this sine squared here. For the sine squared x, I can substitute in 1 minus cosine squared x. Okay, then at least my equation is all in terms of the function cosine. Okay, I'm going to try to set this equal to 0 so I can factor it. Okay, so what I'm going to do, I'm minusing the 1, and I'm going to add the cosine squared to the other side. And no, I don't normally show that step, but I want you to not to see where it came from. So cosine squared x plus cosine squared x is going to give me 2 cosine squared x plus 2 cosine x. The ones cancel. Okay, now I'm equal to 0. Okay, now that I equal 0, I could factor this. I could take out a cosine x or a 2 cosine x. I'm going to take out 2 cosine x. Okay, if 2 cosine x equals 0, then it must be true that cosine x equals 0. If cosine x plus 1 equals 0, then it's true that cosine of x equals negative 1. Okay, now let me look. My domain is actually restricted from 0 to 2 pi. Okay, so my possible answers are, let's see, the cosine is 0 at pi over 2, 3 pi over 2. Okay, that cosine of x equals negative 1, that's at pi. Okay, so it looks like I have 3 answers. However, because I squared both sides, I need to check for extraneous solutions, and I need to check it in the original function. Okay, so let me do a quick check. You don't need to show your check, but you do need to check it or you're going to have extra answers. Okay, so if I do the cosine of pi over 2 plus 1 equals the sine of pi over 2, the cosine of pi over 2 is 0 plus 1. Sine of pi over 2 is 1. Okay, so that answer is good. Let's keep this. Okay, let's try 3 pi over 2. The cosine of 3 pi over 2 plus 1 equals the sine of 3 pi over 2. The cosine of 3 pi over 2 is 0 plus 1. The sine of 3 pi over 2 is negative 1. That does not work. So this answer is extraneous. Let's check our last answer. Okay, the cosine of pi is negative 1. The sine of pi is 0. So this one also works. So in the end, I ended up with the solutions of pi over 2 and pi. 3 pi over 2 ended up being extraneous. Okay, the next type of equation we're going to tackle is multiple angle equations, and then we will save the last type of equation for next class. Okay, multiple angle equations just means instead of having an x, a single x here, I'm going to have a multiple. I have a 2t, I have a 5x, I have an x over 3. Okay, so to start off, I'm still going to isolate the trig function. Okay, so I'm still going to add the 1 over, and I get the cosine of 2t is 1/2. Okay, and then I'm going to think about the unit circle from here. But instead of saying that x equals these solutions, I'm going to say that 2t is equal to these solutions. Okay, and then in my head or on my paper, I'm going to consult my circle. Cosine's 1/2 at pi over 3 and 5 pi over 3. No restrictions, so I'm going to add 2 pi n. Okay, so I know that 2t is equal to pi over 3 plus 2 pi n and 5 pi over 3 plus 2 pi n. I want to actually solve for t. Okay, so I'm going to divide everything by 2 or I'm going to multiply everything by 1/2 to cancel the t out. Okay, so now instead of pi over 3, I have pi over 6. 2 pi n divided by 2 goes down to pi n. Instead of 5 pi over 3, I have 5 pi over 6. Instead of 2 pi n over 2 goes down to pi n. Okay, and then now I've solved for t. Let's try that again with the next one. Oh, except for I can see there's a typo. Okay, change that to cosecant. I'll fix it before class. Okay, I'm going to isolate the cosecant. By adding the 2 over root 3, which means I can reciprocal this. Sine of 5x equals root 3 over 2. Okay, now I'm going to consider the unit circle, but instead of saying x equals, I'm going to say 5x equals. Where is that? That's up here and up here. So pi over 3 and 2 pi over 3. Pi over 3, is there a restriction? No, so 2 pi n, 2 pi over 3 plus 2 pi n. Okay, and then because this is a 5x, I need to cancel the 5. I can divide everything by 5. I can times everything by 1/5. But it's going to go down to pi over 15 plus 2 pi n over 5 and 2 pi over 15 plus 2 pi n over 5. Okay, one last one, and this is just to have a fraction as the value we're solving for. So for tangent, x over 3 plus 4. I'm going to isolate the x over 3 first. Okay, so I'm going to, I'll minus the 4. If I divide by 4, I get -1. Okay, now I'm ready to consider my options here. Okay, instead of saying x equals, I say x over 3 equals 2. Okay, where is the tangent equal to -1? That would be here and here. I could start with either one. 3 pi over 4. Because the period of tangent's pi, I'm just going to say plus pi n. And remember that will capture this answer as well. If you would like to write them separately, you're welcome to do so. Okay, since it's x over 3 though, to cancel the 3, I'm going to times everything by 3. So I will get x equals 9 pi over 4 plus 3 pi n, and that includes all possible values that satisfy this equation.